Okay, so as we talk about limits, as I've mentioned before, we're going to have a lot of techniques for finding limits. One thing to point out, I don't know if I've pointed this out yet or not, is if you try to use direct substitution and you get 0 over 0 as an answer, that is completely meaningless. If you get 0 on the bottom but not on top, then we know that something's happening to make that function undefined, like a vertical asymptote or a hole. However, on the same note, if you get 0 on top, 0 divided by a number just reduces down to 0. However, if I get 0 over 0, that's referred to as an indeterminate form because we cannot determine anything from it. So something to be aware of. So then, talking about the techniques we've learned so far, we've already talked about analyzing from a table or a graph. I put that at the bottom of the list because oftentimes we're not given a graph, and plotting a graph, if we don't have a graphing utility to help us, is very time consuming. Same thing with making a table. It's very time consuming. I put up here number 1 as direct substitution because that's always what we want to try to do first. Unfortunately, a lot of times when we try to do direct substitution, we get this indeterminate form. So that's why we have a lot of other techniques, many of which allow us to manipulate our given equation so that we can use direct substitution. So that brings me to this theorem 1.7 here. Functions that agree at all but one point. So what that is really saying is, can you rewrite your function in another way so that with the exception of that one single value, the functions are completely equal? So for example, maybe there's a hole at that value in one of the functions but not in the other one. Remember, with limits, holes are no big deal, okay? Because we're just talking about what we're getting close to, not what the function actually is. So theorem 1.7 says, suppose that we're having some real number and we have two functions. They are equivalent for every single value except for that C real number in some interval containing C, okay? If the limit of g of x as x approaches c exists, then the limit of f of x also exists and they are the same, okay? So let me show you how that works with this first example. Find the limit as x approaches -3 of x squared plus x minus 6 all over x plus 3. So first thing I notice is if I try to do direct substitution, on top I get 9 minus 3 minus 6 equals, so I'm going to say direct substitution equals 0 over -3 plus 0 equals 0. I don't know what's going on. Okay, so the next thing I'm going to try to do is I'm going to try to rewrite this function in another way. Well, I see on top it's quadratic, so first thing I might try in terms of rewriting in another way is to factor it. So I see I'm going to have x plus 3 times x minus 2 on top. That will multiply to give me x squared plus x minus 6. I still have my x plus 3 on the bottom. Remember, I'm taking the limit. Well, notice what happens now. Now my x plus 3's cancel out. So once my x plus 3's cancel out, I now have the limit as x approaches -3 of x minus 2. Okay, so what is this? This is two functions that are exactly the same at every single point except for at x equals -3. Because in the original function, x equals -3 would be a domain restriction because it makes the denominator 0. So on every single value except for -3, these two functions will be equal to each other. So according to theorem 1.7, if I find the limit of this new function, my original function will have the same limit. So notice with this new function, I can now use direct substitution. So that gives me -3 minus 2, which gives me -5 for my limit. So we will look at a bunch of different ways to manipulate functions and rewrite them, but the number one, easiest one to do is always going to be to look, can I factor it and do some reducing? Because if I can factor and reduce, hopefully I can then use direct substitution.